Hey guys, welcome to the first video. In this video, we're going to be talking about critical stress. So what is critical stress? Critical stress is the stress required to activate a particular deformation mechanism inside of a material. So if we look at the mechanism we're most familiar with, which is plastic deformation, the stress-strain diagram, we have the elastic to plastic deformation. That critical stress for transition between elastic and plastic is what we call the yield stress of the material, and it tells us that dislocations have been activated in the material and are the primary mode for deformation. If we look at this critical stress as a function of temperature, we see that the critical stress for yielding will decrease with increasing temperature. What that tells us is that this area, or the area under this curve, is the safe area for using a particular material. And if we go beyond this yield stress, or this stress in the material, we will then start to incur plastic deformation. And we also learned last class that we have strengthening mechanisms in crystalline materials where we can take that yield stress and we can increase it by using different hardening mechanisms, such as solid solution strengthening, precipitation, cold working, things like that. And what that does is it effectively increases the stress range where we can use that material and shifts that safe zone to higher values. And so that's very important when we're thinking about design and designing different materials. But what about materials that don't just undergo plastic deformation through dislocation motion? Well, if we look at some other materials, such as tin, what we see is that the critical stress for transformation versus the critical stress for deformation versus temperature, we will have a similar response as before for the yield stress for plastic deformation. And so this is all about dislocations. But we will also have another mechanism, which we call twinning. This is the critical stress for twins. If you don't remember what twins are, go back to the defects section of this class or in the book, and you can see what twinning is. It is also a source of deformation. And so what that tells us is that at low temperatures, if we load the material to this particular stress value, we will reach twinning before we reach the critical stress for yielding. And at high temperatures, we will reach the critical stress for yielding before we reach the critical stress for twinning. And what that also means is that our effective region of safely using the material is changed and augmented. It's not just one mechanism that we have to worry about, but two. And this will be shown in a video that I will post, a good demonstration where this is shown to occur in pure tin. Now we can think about the same type of critical stress versus temperature diagram for other types of materials. For example, the dislocation activation critical stress for a metal can be down here, while for a ceramic is much higher. Now, ceramics, we know, typically don't deform through plastic deformation unless we get to very, very high temperatures. And the reason is the material will crack before it deforms. And so if you plot the critical stress for cracking in a material versus temperature, it'll have a response something like this. It looks something like this. So this is for crack propagation. Of course, it's geometry dependent for the crack, but this is to illustrate that ceramics at low temperatures will deform through crack propagation, while at high temperatures they will deform through plastic deformation or dislocation motion. Also, we can see that if we increase the critical stress for plastic deformation in a metal and using hardening, we can make this critical stress for dislocation motion for a metal. This is for a hardened metal. That this can start to interact with the critical stress for crack propagation. And if we increase the strength of a metal high enough, or enough, we will start to have a brittle metal. And this is another way of looking at that ductility versus strength ratio that we discussed in the last class.